You have turned on AQE, you have done your salting, you have set your broadcast joins, and you are still running into bottlenecks with your Databricks notebooks. Repartitioning helps to close that gap, which is move number 3. We have all had the gut reaction to just add more cores, just scale it up. But that hides your problems. Fix the shape of your data. When I say shape, I mean how your rows are laid out across partitions, by which key and how many chunks. Good shape means even work and fewer shuffles across your workers. Bad shape means that one partition drags everything else down, and everybody else has to wait for that one to finish. Now the ops. Narrow ops don't reshuffle data. Select, filter, with column. Wide ops do. Joins on a key, group by, distinct, sorts. Because wide ops shuffle, we fix the shape before we ever do them. Step 1. Set a sane shuffle partition count once. Start around 2 to 4 times your total cores, or size it maybe around 250 megabytes per partition. If tasks finish in a blink, you made too many. Or if they spill or crawl, you've made too few. Step number 2, do one intentional reshape. Repartition on the join key so that the shuffle lands where you want it. Then run your join. Step 3, after you cut the data down, big filter, dedupe, heavy aggregation. Merge your partitions so you don't spray tiny files across all your workers. Coalesce does that merge without another shuffle that Databricks has to handle. Don't double repartition. One reshape with intent, and that's all you have to do. Here's the code and how that looks. Picking your shuffle partition count. As a rule of thumb, 2 to 4 times your total cores, or about 250 megabytes per output partition. Here we're going to use 128 meg. Then let's repartition on the join key before the join. That shapes the shuffle and avoids a random hash spray. That's what we're doing here. We're shaping everything before our wide op. Then we're going to run the wide operation. This is where the shuffle happens. You already set the shape. After a big filter or aggregation, be sure that you coalesce back down. This merges partitions without another shuffle and cuts your tiny files. So that is what we are doing here. Wide op happens here, and we're joining everything back together. Then don't double repartition. One intentional reshape is the play here. And then we put everything back together and we coalesce everything. Okay, we repartitioned the data, but now the data is still huge and continues to burn money in the Databricks furnace. So let's solve that with some caching. Run it twice, pay once. So that's what caching is. You are going to persist, materialize, reuse, unpersist. Dedicated Spark clusters in Databricks support cache and persist. Databricks SQL Serverless does not cache data frames, but it does have SQL level caches. Either way, cache is session only. So be sure to keep that in mind if you are in your notebooks that you cannot persist or cache if you're using serverless, only with dedicated or your classic clusters. Cache things that you're going to reuse. Skip things that you touch once. Size doesn't disqualify a cache. Reuse does. A large data frame that feeds multiple downstream steps might be worth caching. A large one-off won't. So let's look at how you cache your Spark data frame. Here we are persisting the reusable slice at our memory and disk, so it survives the cache churn. Then we're going to materialize it with a count. Now, the first real consumer does not pay the build cost. That's this line here. Then we're going to reuse it in multiple downstream steps. This is where cache really earns its keep. Again, we're running this query once, or setting this data frame once, and then we're reusing it multiple places in our code. And then finally, unpersist when you're done, so that you're giving that memory back so that the next stage doesn't have to spill. So that's this piece right here. Classic and dedicated clusters, cache data frames, Databricks SQL serverless clusters, caches at the SQL layer, not with data frames. So cache where you're actually reusing your data. Now let's check to make sure that our issues aren't at the other end of our pipeline, where it all begins, the I/O. If your table looks like confetti, your reads are going to crawl. Compact and prune your data. Cardinality means distinct values. Partition your low cardinality columns. Use high cardinality columns for filters or Z-order, not discretionary partitions. Cardinality means distinct values. Partition your low cardinality columns and use high cardinality columns for filters or Z-order or liquid clustering, not directory partitions. Target file size on write, compact on a schedule, and turn dynamic file pruning on. Vacuum with your policy. And finally, be sure that you are vacuuming as a policy. Don't over-partitioning explodes directories. 1 to 3 practical partitions is really the sweet spot. So let's take a look at the code and how that might look. All right, start out by controlling your file size on write so that you don't create that file confetti. Larger, consistent files speed up scans. Next, you're going to turn on dynamic file pruning. Spark skips files that cannot match your filters. You have Optimize, which compacts small files. Use Z-order on a common filter column to cluster the data for faster range reads. And then you have Vacuum, which cleans old files after the retention window. Built-in functions beat SQL strings, which beat Pandas UDFs, which in turn beat Python UDFs. Be sure that you're pushing your work into the right engine. Turn on dynamic partition pruning for big star joins to skip partitions automatically. Check pointing is more reliable than cache. Aggregate before you explode when possible, and fewer rows means fewer shards to blow up later. All right, here's some interview ammo. How do you detect skew and choose adaptive versus salting? Here's your rapid fire answers. Skew versus salting. If AQE splits cleanly, write it out. If not, salt the hotkeys and unsalt after. Repartition versus Coalesce. Repartition once before wide ops to set the reshuffle. After big filters, be sure that you're coalescing to cut the file counts. Next, grab the PySpark 202 cheat sheet. It has the skew checklist, the broadcast rules, the pre-partitioning of the tables, compaction steps, everything we've talked about. Use it tonight, and then circle back to the dedicated versus serverless question. That is the biggest question that you get asked in Databricks. To hear the decision matrix I use, check out this video right now.